Hello, my AP Chemers. We are talking about electrochemical cells, and today we're going to look at delta G and Gibbs free energy and its relationship to the cell potential. So remember, the cell potential is the voltage of your cell. Gibbs free energy is a thermodynamic variable that determines the spontaneity of a reaction. So remember that electrochemical cells are spontaneous. That means Gibbs free energy is negative. They are product favored. So for an electric cell to run spontaneously, the potential must be positive, meaning that the charges will always go towards the positive potential. And so your electrons are flowing in the correct direction. This reaction is favorable. It is spontaneous. It is going to happen. And so that means that delta G is negative and your cell potential is positive. So for any electrochemical cell, delta G negative, cell potential is positive. The relationship between delta G, Gibbs free energy, and the cell potential is this right here. So the Gibbs free energy for a reaction at standard conditions is equal to negative NFE. So let's go through each one of these variables. So this is the Gibbs free energy. And it's usually measured in kilojoules per mole. N is the number of moles of electrons transferred. So what does that mean? That means when you balance your reaction, remember how we equalize the number of electrons because one species is losing the electrons, the other one is gaining the electrons. So when you're balancing, the final number of electrons that you cross out, that is your number for N here. Then F is Faraday's constant. Which is equal to 96.5 kilojoules per mole volt. And then E is, of course, your cell potential, and it's measured in volts. And remember, the little degree sign just means that you're at standard conditions. So let's try a problem where we can calculate delta G. So we want to calculate delta G for this right here. If this was on the test, you'd be also given some reduction potentials as well. So what you would do is you would say, okay, well, I have zinc getting oxidized to zinc 2+. I have copper 2+ being reduced to neutral copper. So I gain 2 electrons here, I lose 2 electrons here. I need to look up your potentials for both of these processes. I'll start with the copper one. This is a reduction, so I look it up as is from my reduction potentials, and it is positive 0.34 volts. For my zinc, this is an oxidation, and so for oxidation, I flipped my reaction, so I also flip my potential. So the reduction potential for zinc is negative 0.76. The oxidation potential would be positive 0.76 volts. And so the cell potential total is going to be 1.10 volts. And of course, this is at standard conditions. So to calculate Gibbs free energy, I'm going to say delta G naught is equal to negative NFE naught. So delta G naught is equal to negative. My number of electrons that are transferred are this number right here, and they should match. So that is 2 moles of electrons. My Faraday's constant is 96.5 kilojoules per mole volt. This is moles here. And my cell potential I just calculated to be 1.0 volts. So my Gibbs free energy ends up being negative 212 kilojoules. So just to double check, if this was a spontaneous reaction, which it is, your cell potential needs to be positive, your delta G needs to be negative. Both of them check, so that means that we probably did it correctly. So this is at standard conditions. That little degree sign means standard conditions. So what if you're not at standard conditions? So standard conditions mean 25 Celsius, which is room temperature, 1 molar solutions, and 1 atm of pressure. So if you were to calculate Q, the reaction quotient, whether you're looking at concentrations, if they're all 1 molar and you're doing products over reactants, no matter raised to what power, 1 over 1 or times 1 or squared or whatever, it's going to be 1. Same thing with 1 atm if you're doing in terms of pressure. Since all of them are 1 atm, then you're also going to get 1. So at standard conditions, the reaction quotient is equal to 1. Again, whether it's in terms of concentration or in terms of pressure. If your value of Q changes, then your cell potential is going to change. So when Q is equal to 1, we're at standard conditions, and so the cell voltage is equal to whatever it is at these standard conditions. You look that up from the table, you add your both of the potentials for both of your half reactions, add them together to get your cell potential. If Q is smaller than 1, remember Q is the ratio of products to reactants raised to the power of their coefficients, right? Whether it's in terms of concentration or pressure. So if Q was too small, was smaller than 1, that means that you don't have as many products. Your products are too few, or your reactants are too many. So you don't have enough products. And so that's going to make the driving force for the reaction increase so that you make enough products. And so it's going to make your cell more product favored than at standard conditions. And so your voltage is going to get higher because it's going to be more spontaneous, more product favored. Your delta G will become more negative and your cell potential will be more positive. Will be a bigger positive number. Your delta G will be a bigger negative value. However, if your Q is greater than 1, then that means you have too many products. This ratio is too high. And so you have too many products or you have too few reactants. And so that's not good. So the driving force for the reaction is going to decrease. It's not going to go towards the product as much. It's going to be less product favored. And so your cell potential will still be positive, but it's going to be a lower positive number. Your Gibbs free energy is still going to be negative, but it's going to be a lower negative value. The reaction is still going to be product favored, but it's going to be less product favored. And so your cell potential will be lower. Now, here, this is pretty important. When you are talking about electrochemical cells, you cannot use Le Chatelier's principle to explain whether your cell potential will be higher or lower at non-standard conditions. You may not use Le Chatelier. You have to use this Q explanation because Le Chatelier means you've reached equilibrium already and then you've stressed your system and it's going to go one way or the other. With electrochemical cells, they can never proceed towards the reactants. They will always proceed towards the product. Otherwise, it's not an electrochemical cell. Otherwise, it's not spontaneous. Electrochemical cells have to be spontaneous. Once you reach equilibrium, your battery is dead. So it's always going to be product favored. The question is it more product favored or is it less product favored? But it's always going to be product favored if it's an electrochemical cell. So be careful with your wording when it comes to this one. It does not make it go to the left. It does not make it reactant favored. It is still product favored. It's just less product favored. Your cell potential is still positive. It's just a smaller positive value. Your delta G is still negative because it's spontaneous. It's just a little bit less spontaneous than what it would be at standard conditions. So let's look at this here. In this cell, which is the one that we've just talked about, with 1 molar concentration, the electric potential is 1.10 volts. We calculated that, right? What will happen to the cell potential if I increase my Cu2 plus concentration? Well, remember that Q is products over reactants. So if I have too many reactants, if I increase my reactants, too many reactants, that means my Q is less than 1. And so it's going to be more product favored. The driving force for the reaction is going to increase to make more products. And so my cell potential is going to increase. It's going to be a bigger positive value. My delta G is going to be a more negative value. Say higher positive value. And my reaction will become more spontaneous. Okay, let's say that the zinc 2 plus concentration increases. So what's going to happen? Well, zinc here is a product. So if I increase my Zn2 plus concentration, then I have too many products. My Q is greater than 1. My product to reactant ratio is greater than what it normally would be. And so the driving force for the reaction is not going to be as high because I have already too many products. It doesn't want to make more products. And so it's going to be less product favored. Again, you don't want to say it's reactant favored. It's still product favored. It's just less product favored. Your cell potential is going to decrease. It's going to be a lower positive value still. Still positive, still spontaneous. Delta G is going to be a lower negative value. It's still going to be negative, but it's going to be a lower negative value. It's still spontaneous, but it's going to be less spontaneous. So there's a way to calculate what the cell potential would be at non-standard conditions. And the way that you do it is using the Nernst equation. And the Nernst equation is actually still on the green sheet, but College Board says they're not going to ask you to calculate it. They will ask you about it qualitatively. But let's look at the Nernst equation because you'll definitely probably use it in college. So we said that in the previous chapter that delta G at non-standard conditions is equal to delta G at standard conditions plus RT ln of Q. And we just said in the previous page that delta G naught is equal to negative NFE naught. If you're not at standard conditions, then you can say delta G at non-standard conditions is equal to negative NFE at non-standard conditions. So if you plug this in for the delta G naught, and you plug this in for the delta G, then this is what you get. If you rearrange this a little bit, you would get this equation. If you take this R, which is a constant, and this F, which is a constant, and actually plug in your values, this is what you would get. You can also express it with logs instead of natural logs, and on the green sheet it is with the natural log, but not the log-based stuff. But those are what the Nernst equation are. And again, this is on the green sheet. You can refer to it, you can use it qualitatively, but they will not ask you to calculate things with it. But this is how you would calculate what the E cell would be at non-standard conditions. You'd need to find what it is at standard conditions, you'd need to find Q, and you'd need to figure out how many moles of electrons are transferred. So again, if you want to use this as in terms of driving force to explain what happens to your cell potential at non-standard conditions, you can. here it is using the Nernst equation, explaining it with the Nernst equation. So if Q, this Q here, is equal to 1, then natural log or log of Q would be equal to 0. And so this whole term would be equal to 0. So the cell potential at non-standard conditions will be equal to the cell potential at standard conditions, right? If Q is less than 1, this number is less than 1, then the natural log of Q would be a negative number. And so subtracting a negative number would make it positive. So you would take your standard cell potential and add a positive number to it. And so your cell potential would be a higher value. If Q is greater than 1, this number is greater than 1, then natural log of Q would be a positive value. So you're subtracting a positive value from your standard cell potential, and so your cell potential at non-standard conditions, the E cell, would be lower than what it is at standard conditions. So you could use this explanation using the Nernst equation, using math, or you can use talking about too few products or too many products and talking about the driving force. They're both valid explanations. Just never use Le Chatelier's principle, and never say that it is not spontaneous, or that it's going to the left, or that it's reactant favored. It's always going to be product favored. Let's look at this here. So we have, we want to calculate the electric potential for the following cell under standard conditions. And we're given the reduction potentials. So here we first, if it's an electrochemical cell, we have to figure out which one's oxidized, which one's reduced. And so this one has a higher reduction potential. So this one, the lead, is going to be reduced. And the cadmium has a lower reduction potential. That means it's going to be oxidized. So we have Pb2 plus 2 electrons yields Pb. This one's as is, negative 0.13 volts. But the other one would be the flip. Cd yields Cd2 plus 2 electrons. And because we flipped it, we're going to flip the potential, so positive 0.40 volts. And so altogether you get 0.27 oops. .27 volts is your cell potential at standard conditions. Okay, the question next is, how is the cell potential affected when the cadmium concentration changes to 0.01 molar and the lead ion concentration changes to 0.1 molar? So remember that at standard conditions, all of these are at standard conditions, which means 1 molar solutions. So we are changing both of them. Let me add these two together. Cross that out. So, oops, cross this out with the electrons. So we get the overall equation is Pb2 plus Cd yields Cd2 plus Pb. So what I'm doing is I'm dropping the concentration of the cadmium ion. I'm also dropping the concentration of the lead ion. So would it not change? Well, we're not dropping them with the same amount, right? Which one is lowering even more? Well, this one's going from 1 molar to 0.1 molar, tenfold. This one is going from 1 molar to 0.01 molar, 100-fold. So we are dropping the cadmium concentration way, way, way more than we are the lead ion concentration. So how does that affect things? Well, if I'm dropping this a lot more, then that means that I have too few products. And so if I have too few products, it's going to become more driven to make more products, and your cell potential would increase. So your Q would be less than 1, and so it's going to be more product favored. Your cell potential would increase. And of course, your Gibbs free energy would become a larger negative value. It's going to become more spontaneous. So let's look at equilibrium. What does equilibrium mean for a battery? Well, at equilibrium, that means your battery is dead. When you've reached equilibrium. Also, we know at equilibrium that delta G is equal to 0, Q is equal to K, and you have no more voltage in your battery. Your cell voltage will be 0 volts. And so if we plug this K for Q here and we plug 0 here, we've done that last chapter, we would get that delta G naught is equal to negative RT ln of K. We've used this in the last chapter, in the previous chapter. We also would plug in 0 for the E cell. And so if we rearrange this to solve for the cell potential at if we plug in 0 here and rearrange it, then you would get this equation right here. Natural log and log base 10. So we can use this to either calculate the cell potential if we're given K, or to calculate K if we are given the cell potential. So let's look at this question here. It says, construct the cell between iron and cadmium. Iron is going to be oxidized, cadmium is going to be reduced, and determine the equation for the cell under standard conditions. And we also want to determine the equilibrium constant for the reaction. So construct it means draw it. So let's practice drawing the reaction here. So we have our anode and cathode. I'm going to do a semi-permeable membrane here instead of the two beakers. So this is the anode, cathode. So same thing here, anode, cathode. So this is my iron metal, this is my cadmium metal. And my solutions here, this is Fe2+, this is Cd2+, and of course you need some nitrates or something like that for your solutions. You need a wire to connect the two, and you don't need a salt bridge if you have a semi-permeable membrane. That's where your nitrates would move. That's where your anions would move. So we've constructed the cell. We also want to determine the equation for the cell, and so we have Fe yields Fe2+ plus 2 electrons. We also have Cd2+ going to Cd, so we'd need 2 electrons here. Let's look at the cell potentials. This is oxidation, this is reduction. So the reduction, we're going to write it as is on the table. The cadmium one, the cell potential is negative 0.40 volts. For the iron, it is negative 0.44 volts, but if we're oxidizing it, then we flip it, so positive 0.44 volts. And so electrons cancel. My overall equation is Fe plus Cd2+ yields Fe2+ plus Cd, and my cell potential is going to be positive 0.04 volts. And it's positive because it's an electrochemical cell. The last thing we need to figure out is the equilibrium constant. So we're going to use this equation right here to get the equilibrium constant. So we're going to do E cell is equal to 0.0257 natural log of K over N. And so our cell potential is 0.04 volts. That is equal to 0.0257 natural log of K over N, remember, is the number of moles of electrons that are transferred. And so the electrons that you cross out, that's the number of electrons. So that's 2. And we're going to solve for K. I got that K is equal to 22.5. And K should be greater than 1 if it is product favored. So that matches as well.